And I'm Dejanira Aranda. Today, we are excited to present a unique perspective on a paradox generally associated with human systems. But what would you think if we told you this paradox could also appear in the natural world, particularly among fish?
Together with our colleagues, Dr. Palestina Guevara Fiore and Dr. Felipe Pacheco Vázquez, we've been investigating how the Braess paradox manifests in the behavior of guppies. Our presentation is titled Which Way Should I Go? Braess paradox in guppies, Poecilia reticulata. But first, what exactly is Braess paradox?
Braess paradox is a phenomenon in network theory where adding extra capacity, such as a new road in a traffic system, can paradoxically worsen overall performance by increasing congestion.
This happens because individuals acting in their own self-interest change routes to use the new option, which ultimately causes inefficiencies and bottlenecks. This phenomenon shows that more options don't always improve flow and can sometimes have the opposite effect. For example, imagine you are in a city with two main routes and traffic flows smoothly. Then the city builds a new shortcut between these two routes.
You'd think this shortcut would help people reach their destinations faster, but in many cases, more people use this road, causing traffic jams. Ultimately, everyone might spend more time on the road than before the shortcut was built.
Since German mathematician Dietrich Braess described this paradox in 1968, it has been studied in various contexts: computer, electrical and mechanical networks, and biological systems such as blood vessels and metabolic pathways. However, it has yet to be explored in the context of animal movement or behavior. Our research aims to study this paradox in guppies and understand how environmental changes and network structures influence animal social and collective behavior. To do this, we must consider guppy collective behaviors, specifically shoaling. But why is this important?
Shoaling and schooling are social behaviors in fish, but they differ in their level of coordination. Shoaling is a loose gathering of fish that stay together for social reasons, like protection, feeding, or mating, without any strict synchronization. On the other hand, schooling is a tightly coordinated group where fish swim in unison, moving together as one. While both behaviors offer protection from predators, shoaling focuses more on maintaining social proximity, whereas schooling maximizes efficiency and confuses predators through precise, coordinated movements.
Female behavior in guppies is fascinating. Female guppies form more cohesive groups than males, with stronger social bonds and tighter coordination with their shoals. In contrast, males tend to be more competitive and solitary, focused on mating, resulting in looser social groupings with less cohesion.
When it comes to decision making, guppies often act collectively, especially in social contexts like foraging or avoiding predators. Their decisions, such as which direction to swim or how to react to threats, are influenced by both individual assessments and group dynamics. Social cues, such as the behavior of other guppies, play a crucial role, with individuals often following the majority or more experienced members to reduce risk.
In guppies, highlight social behaviors are observed, including group foraging. They also show differences in the intensity of their responses to certain gustatory stimuli. Social interactions and responses to stimuli highlight the relevance and the complexity of the collective dynamics of their behavior and the learning processes within the group.
Finally, both preference and panic significantly influence Guppy decision-making. In calm situations, Guppies rely on their preferences, such as following familiar individuals or seeking better feeding spots. However, when faced with sudden threats, panic can override these preferences, leading to faster, less coordinated decisions as guppies prioritize escaping over social bonds or exploration.
This is why our goal is to study this paradox in experimental models where both preference-based motivation and panic play a significant role. For this, we designed two different experiments.
For both experiments, we use an 80 by 30 by 30 centimeters tank divided into an experimental zone and an open field zone by an opaque black acrylic wall with one or two openings depending on the treatment. We tested three experimental conditions: one opening on the left side, one opening on the right side, and two centered openings. First, we will explain to you the experiment in panic conditions. For this experiment, we placed two black walls and a funnel in the experimental zone to reduce the available space, forcing the fish to cross the opening. Here you can see a view from above the tank to appreciate the position of the funnel. Before the start of the trial, a transparent wall blocked the opening to prevent the fish from passing into the open field zone. A movable wall, gently pushed by a mechanical arm at a speed of 7 millimeters per second, moved from the tank's edge to the funnel's entrance. The fish acclimated for 10 minutes in the tunnel. Then we activated the mechanical arm, removed the transparent wall, and recorded the trials until the mechanical arm finished its course. We performed 6 trials with 60 female guppies for each experimental condition, for a total of 18 trials. We didn't use the fish for more than one trial. We analyzed the videos frame by frame for the experiments in panic using the software Braess to quantify fish flow. We analyzed the data by generating frequency distribution graphs, followed by analysis using the Kolmogorov-Smirnov test. Preliminary results from the panic condition trials indicate that the flow does not change significantly over time between the three treatments, suggesting that the Braess paradox is present. However, the distribution of the flow in the same amount of time seems to be different, with the opening on the left side having an exponential distribution, while the opening on the right side has a linear distribution. In addition, we can observe that when there are two openings, the fish prefer to go through the right opening instead of using both sides. This could be partially explained by laterality, but we need to conduct more trials to have a better representation of the behavior of this species in these experimental conditions.
Now, we will explain the second experiment involving presence-based training to you. We conducted the preference-based training experiment with three groups of 65 fish training using different opening positions in the dividing wall and two types of food with varying preference levels as motivation to cruise through the openings. The preferred food was tetramine tropical flakes and the less preferred food was freeze-dried Tubifex. We test 6 treatments, considering the opening position and type of food, as shown in the matrix. We repeated each trial twice per group, after a 15-minute acclimation period during which the fish could smell the food. The trial began by removing the transparent wall, allowing the fish to flow. Using high-resolution cameras, we recorded fish behavior from the front and top views for 2 minutes and 30 seconds. We conducted a frame-by-frame analysis using Braess software to quantify the number of fish crossing into the feeding zone every 3 seconds during the first 30 seconds of recording. Using the data extracted from the videos, we fitted an exponential decay model based on Malthus equation to describe how the fish population in the experimental zone decreased over time. This model allowed use to observe the decay rate and fish flow over time for each opening. Additionally, we applied a GLMM to assess difference in fish flow across various opening types and motivation levels. We conducted the analysis in RStudio. The Braess paradox is present in our system. Fish flow did not change between 1 and 2 openings. As predicted, adding a second opening in the system did not proportionally increase fish flow, which was validated by fitting our Malthus model. The decay rates in fish flow across the different openings, left, right, and both, were not different. This supports confirmation of the paradox presence. In the graph, you can observe the model's predicted fish flow and the observed flow from the trials, show as solid and dotted lines respectively, confirming the model's accurate fit to the flow dynamics in our system. The GLMM result showed that flow through one opening did not change compared to two openings, further confirming the presence of the paradox. It also revealed that, contrary to our prediction, the flow between the preferred and less preferred food showed no differences, suggesting that motivation did not alter the paradox presence. Lastly, the interaction between one opening with low motivation and two openings with high motivation also showed no differences in flow, reinforcing that the number of openings and food motivation did not affect flow.
The results indicate that the Braess paradox is present in the collective swimming of guppies, as adding an opening did not increase the flow proportionately as expected. Food preference and panic did not influence this dynamic. Group lateralization could be a key factor, as it limits the system's efficiency with two openings by triggering an individual decision-making process, potentially reducing flow efficiency. These results suggest that, similar to inert systems, more routes in biological systems do not always improve flow efficiency.
We would like to thank Dr. Palestina Guevara Fiore and Dr. Felipe Pacheco Vázquez for being outstanding advisors. We would also like to thank the whole team at the Laboratorio de Ecología Evolutiva WAP for their immense help.
Now we would love to answer any questions you have. So what questions can we answer for you?
So here I am. Let me stop this. Sorry again for this little problem with the presentation.
It's a little bit, the audio is a little bit like weird.
Oh, sorry, during the presentation. So we can ask question now. So the question are arriving. I have a question for you. Would you expect a difference between males and females in this behavior? Like, do you think you would see difference in the behavior between in this paradox between males and females if you separate the guppies?
Yes, females are more cohesive and males tend to be to have more audacity. So if we use both males and females, we would have maybe a difference. That's actually it's part of my PhD work.
Perfect. We have a question from Valentin on YouTube. If I recall correctly, in human evacuation systems, it was found that placing an obstacle before the exit door improves the flow, Do you think this could be an extension of your nice experiment?
Yes. Yes. There's that's a possibility. But I don't think the experimental design is going to allow us to do that because of the tunnel and the funnel and everything. But it actually, it's proven to improve flow.
And so we have a comment from Valentin that is saying that he really enjoyed your slides, great presentation. We also have a question from Eddie. Great talk. Do you think changing the configuration of entrances will have an effect? For example, if you have two barriers, one after the other, one with a single entrance and another with two?
I'm sorry, it's a little bit choppy. Could you
Yeah,
please repeat it?
I can say the question again. It's because of my computer. Do you think changing the configuration of the entrances will have an effect? For example, if you have two barriers, one after the other, one with a single entrance and another with the two entrances, would it change something in the flow?
No, these fish are only used once.
Oh.
They do not go through repetitive trials. They just are used for one, and that's it. So
But
they do not go through.
But if you have two barriers instead of one, do you think you would see a difference with the choice they made, like one barrier and then another barrier? Would you just choose a different way to go out, or?
I think he did something like that. ¿Tú pusiste dos barreras? Sí, porque pusiste una 5 centímetros antes.
But
No,
it would be good to try, I think.
Yes, that would be different. I don't know, but it's interesting.
Well, thanks a lot for the great presentation. I'm sorry again for the problem with my computer. And you can go on Discord. I think you will have much more questions. And it's now time for a little break before the other presentation. During this break, you can leave the session if you want now.